Hello everyone, this is lecture 3 part 1. We will talk about forward kinematics and the Dennevit-Hardenberg convention. Let's now think, what is kinematics? Kinematics is the science of motion that treats the subject without regard to the forces that cause it. Within the science of kinematics, one studies the position, the velocity, acceleration, and all higher order derivatives of the position variables with respect to time or any other variable. The forward kinematics problem is concerned with the relationship between the individual joints of the robot manipulator and the position and orientation of the tool or end effector. The forward kinematics problem is to be contrasted with the inverse kinematics problem, which is concerned with determining values for the joint variables that achieve a desired position and orientation for the end effector of the robot. Let's go to the link description. A manipulator may be thought of as a set of bodies connected in a chain by joints. These bodies are called links. Joints form a connection between a neighboring pair of links. The joints can be either very simple, such as a revolute joint or a prismatic joint, or else they can be more complex, such as a ball and socket joint. Here you see the graphical pictures of a rotary joint, a prismatic joint, and a hook joint. A rotary joint is the joint angle about the joint rotation axis Z, describes the joint displacement. Prismatic or sliding joint, the linear displacement d along the joint axis Z describes the displacement. And in hook joint, this is a 2 degree of freedom rotary joint described by two rotation angles, for example yaw and pitch. Thus, a hook joint is represented by two consecutive rotary joints with the intersecting rotation axes. Next we see the spherical joint, a roll pitch roll and a roll pitch yaw equivalents of the spherical joint. Three joint angles about three rotation axes are required to describe this displacement about the spherical joint. A spherical joint can be represented by three consecutive rotary joints with intersecting rotation axes. There are many ways to configure three such rotary joints. The human shoulder and wrist are spherical joints. Most robot wrists are spherical joints with one or two arrangements. Roll pitch roll wrist, in this equivalent, in their zero positions, the first and third rotation axes are parallel and the second axis is perpendicular to them. Hence, the first and third axes may be considered to generate roll motions, while the second generates a pitch motion. You can see this in picture B. A disadvantage is that the wrist singularity is located in the pointing direction. An advantage is that motors can be separated into the forearm, wrist and hand. And now the roll pitch yaw wrist equivalent. Here in their zero positions, the rotation axes are at right angles and may be considered to be described by roll pitch yaw angles. A disadvantage of this wrist is that motors would seem to have to be coincident. An advantage is that the wrist singularity, a degeneracy of alignment of two axes, is at right angles to the pointing direction. A link is considered only as a rigid body that defines the relationship between two neighboring joint axes of a manipulator. Joint axes are defined by lines in space. Joint axis I is defined by a line in space or a vector direction about which link I rotates relative to link I minus 1. It turns out that for kinematic purposes a link can be specified with two numbers which define the relative location of the two axes in space. For any two axes in 3 space, there exists a well-defined measure of distance between them. This distance is measured along a line that is mutually perpendicular to both axes. This mutual perpendicular always exists. It is unique except when both axes are parallel. in which case there are many mutual perpendiculars of equal length. You can see this description in the picture below. The figure shows link I minus 1 and the mutually perpendicular line along which the link length A I minus 1 is measured. Another way to visualize the link parameter is to imagine an expanding cylinder whose axis is the joint I minus 1 axis. When it just touches joint axis I, the radius of the cylinder is equal to I minus 1. The second parameter needed to define the relative location of the two axes is called the link twist. If we imagine a plane whose normal is the mutually perpendicular line just constructed, we can project the axes I minus 1 and I onto this plane and measure the angle between them. This angle is measured from the axis I minus 1 to axis I in the right hand sense about alpha I minus 1. We will use this definition of the twist of link I minus 1, alpha I minus 1. In the figure, alpha I minus 1 is indicated as the angle between axis I minus 1 and axis I. The lines with the triple hash marks are parallel. In the case of intersecting axes, twist is measured in the plane containing both axes, but the sense of alpha I minus 1 is lost. In this special case, one is free to assign the sign of alpha I minus 1 arbitrarily. Let's see what planar pairs means. A planar pair is any combination of three rotary and prismatic joints that generate motions of the plane. For example, x, y translations and planar rotation. Two common planar pair combinations are RRR or triple R planar pair. This is a planar pair constructed for three consecutive rotary joints whose axes are all parallel. A planar three-link manipulator is the equivalent result. RPR planar pair, a rotary joint is followed by a prismatic joint, which is followed by a rotary joint. All three axes are parallel. You can see here the planar pair, and in B the three rotary joint equivalent. Let's now go to our main issue for this lecture, the setting up of coordinate systems in the links, and of course the Denavit-Hardemer coordinates. We need to set up a coordinate system in each link in order to define transformations between links and ultimately the location of the end link relative to the base of the robot. There are a variety of ways of defining such coordinate systems. We could, for example, set up coordinate systems in each link arbitrarily, then define a transformation I minus 1 Ti between links I and I minus 1. However, the method of defining coordinate systems should take into account constraints imposed by the joint type. In robotics, we typically deal only with rotary and prismatic joints. The 6 numbers 3 position, 3 orientation for arbitrary coordinate system placement in a link are too many because neighboring links don't undergo arbitrary relative motion to each other. Prismatic or rotary joints allow only certain motions between links, and hence fewer than 6 numbers are required to locate a link's coordinate system. We will see that in the next few slides. Let's see how we define the numbers of Denavit-Hardemer convention for the intermediate links in the chain. Neighboring links have a common joint axis between them. One parameter of interconnection has to do with the distance along this common axis from one link to the next. This parameter is called the link offset. The offset at joint axis I is called di. The second parameter describes the amount of rotation about this common axis between one link and its neighbor. This is called the joint angle, or theta I. We will see this in this picture, that is a link chain. In this figure, it is shown the interconnection of link I minus 1 and link I. Recall that AI minus 1 is the mutual perpendicular between the two axes of length I minus 1. Likewise, AI is the mutual perpendicular defined for length I. The first parameter of interconnection is the length offset di, which is the signed distance measured along this axis of joint I from the point where AI minus 1 intersects the axis to the point where AI intersects the axis. The offset di is indicated in the figure. The length offset di is variable if joint I is prismatic. The second parameter of interconnection is the angle made between the extension of AI minus 1 and AI measured about the axis of joint I. This is indicated in figure where the lines with the double hash marks are parallel. The parameter is named theta I and is variable for a revolute joint. For the first and last links in the chain, link length AI and link twist alpha I depend on joint axes I and I plus 1. Hence, A1 through A n minus I and alpha 1 through alpha n minus I are defined as was discussed in this section. At the end of the ends of the chain, it will be our convention to assign 0 to these quantities. That is, A0 equals AN equals 0 and alpha 0 equals alpha n equals 0. Link offset di and joint angle theta I are well defined. For joints 2 through n minus 1 according to the convention discussed in this section, if joint 1 is revolute, the 0 position for theta 1 may be chosen arbitrarily. D1 is equal to 0 will be our convention. Similarly, if joint 1 is prismatic, the 0 position for D1 may be chosen arbitrarily. Theta 1 equals 0 will be our convention. Exactly the same statements apply to joint N. Now, how we affix frames to links. For intermediate links in the chain, the convention we will use to locate frames on the links is as follows. The z-axis of frame I, called Zi, is coincident with the joint axis I. The origin of frame I is located where the AI perpendicular intersects the joint I axis. Xi points along AI in the direction from joint I to joint I plus 1. In the case of AI equals 0, xi is normal to the plane of zi and zi plus 1. We define AI as being measured in the right-hand sense about, and so we see that the freedom of choosing the sign of AI in this case corresponds to two choices for the direction of xi, yi is formed by the right-hand rule to complete the ith frame. For the first and last links in the chain, we attach a frame to the base of the robot or link 0, called frame 0. This frame does not move. For the problem of arm kinematics, it can be considered a reference frame. We may describe the position of all other link frames in terms of this frame. Frame 0 is arbitrary, so it always simplifies matters to choose Z0 along axis 1 and to locate frame 0 so that it coincides with frame 1 when joint variable 1 is 0. Using this convention, we will always have A0 equals 0, alpha 0 equals 0. Additionally, this ensures that D1 equals 0 if joint 1 is revolute, or theta 1 equals 0 if joint 1 is prismatic. For joint n revolute, the direction of xn is chosen so that it aligns with xn minus 1 when theta n is equals 0, and the origin of frame n is chosen so that dn equals 0. For joint n prismatic, the direction of xn is chosen so that theta n equals 0, and the origin of frame n is chosen at the intersection of xn minus 1 and joint axis n when dn equals 0. For a summary of link frame attachment procedure, the following is a summary of the procedure to follow when faced with a new mechanism in order to properly attach the link frames. First, identify the joint axes and imagine or draw infinite lines along them. For steps 2 through 5 below, consider two of these neighboring lines at axes I and I plus 1. Second, identify the common perpendicular between them, or point of intersection. At the point of intersection, or at the point where the common perpendicular meets the ith axis, assign the link frame origin. Third, assign the zi axis pointing along the ith joint axis. Fourth, assign the xi axis pointing along the common perpendicular, or if the axes intersect, assign xi to be normal to the plane containing the two axes. Fifth, assign the yi axis to complete the right-hand coordinate system. Sixth, assign 0 to match 1 when the first joint variable is 0. For n, choose an origin location and xn direction freely but generally so as to cause as many linkage parameters as possible to become 0. Now we will see an example of triple arm mechanism. This is a 3-link planar arm. On the right we saw the same manipulator by means of a simple semantic notation. Hash marks on the axes indicates that they are mutually parallel. We start by defining the reference frame, frame 0. It is fixed to the base and aligns with frame 1 when the first joint variable theta 1 is 0. Therefore, the position frame 0 as shown in the figure 3.7 with z0 aligned with the joint 1 axis. For this arm, all joint axes are oriented perpendicular to the plane of the arm. Because the arm lies in a plane with all z-axes parallel, there are no link offsets, and all di's are 0. All joints are rotational, so when they are at 0 degrees, all x-axes must align. We see here the Denavit-Hardenberg table. Please try yourselves to solve this using the right-hand method. Any problems will be discussed in the forum. But I would like lastly to note that because the joint axes are all parallel and all the z-axes are taken as pointing out of the paper, all alpha i's are 0. This is obviously a very simple mechanism. Note also that our kinematic analysis always ends at a frame whose origin lies on the last joint axis. Therefore, L3 does not appear in the link parameters. So this was an introduction to the Denavit-Hardenberg coordinate systems. In the next session, we will see how we can solve a forward kinematics problem by using a Denavit-Hardenberg table. So I would like you to study these slides and the additional notes that will be posted in the forum very carefully. Thank you all very much.